So, the last speaker today is David Levin from University of Oregon, who's going to finish off the talk on the Ising Model.
Okay, thank you. Thanks to the thanks for the organizers for the invitation. I promise to try to be very brief. It's late in the afternoon. Okay, so I'm continuing to report on this joint work with Malvina Lushak and Yuval Perez. Okay, so I just want to, well, maybe I go very fast through this, since this is at least the third or fourth time today we've seen this Ising measure. So, you have the energy, which is the product of the sum of spins. Here I'm working on the complete graph. So so there are n sites, and everybody's a neighbor of everybody else. So you're summing over all pairs of vertices. And here you want the total interaction to be of order 1. So the relative parameter here is beta over n. Okay, so again, we're doing Glauber dynamics, so we're picking sites uniformly at random, and you update the spin at that site to either a plus or minus 1. And the probability of putting a plus 1 there is determined by the conditional probability of putting a 1 there given the neighbors. Here everybody's a neighbor except the vertex you select itself. So the relevant statistic is not the total sum of spins, the magnetization, but rather that minus the spin at the site that you're updating. So I'm going to work here with the average magnetization, so I'll roll this constant 1 over n into the magnetization. Okay, so I think everyone is up to date on this Markov chain. Okay, so I just want to explain where this power of 3/2 comes from in the critical case here. So critical means beta equals 1, and where does this 3/2 come from? So we've seen the n log n mixing for high temperature, and as Eric explained this morning, at least for colorings, this is because you have a contraction in that case of the Hamming distance between two configurations. Malvina discussed this case where you truncate the dynamics even when you're in the supercritical case, and there it's because you have some hitting time estimates. And if you don't truncate, you have exponentially slow mixing. So why this 3/2? And I just try and say very briefly where this power of 3/2 comes from. Okay, so that's the plan. All right, so the proof again uses coupling. So this is the basic technique here. And so we want to have 2 copies of this, either the magnetization, the total magnetization, the sum of the spins. I can't remember, in some places I worked with the average magnetization, so I divided this by n. And the key thing here is that when beta equals 1, it takes order n to the 3/2 steps for this magnetization to hit 0. And okay, so that's how long it takes, just 1 copy of the chain. So there's no coupling in this statement. But once you know that you can get 1 copy of the chain to hit 0 in n to the 3/2 steps, or order n to the 3/2 steps, you can use a very simple coupling called the reflection coupling, which I'll mention briefly, to show that you can couple together any 2 copies of the chain so that they hit in this order of n to the 3/2. Okay, and then I just appeal to a general lemma. It's true at any temperature that in the complete graph. Once you get the magnetizations to agree, then it takes only order n log n more steps to get the full configurations to agree. So, and that holds at any temperature. And since we're just looking for a power of n to the 3/2, n to the log n is of smaller order, so the key thing here is getting the magnetizations to agree. And so that's what enables you to do this. Okay, so as I mentioned, where does this n to the 3/2 come from? Well, it's the time it takes for the magnetization chain to hit 0. Okay, so when I'm analyzing the amount of time it takes, at least with high probability, to hit 0, there's 2 phases. One is you want the average, the expectation of ST to be small, But at some point, the expectation of ST becomes of the same order as its fluctuations, in which case waiting longer for the expectation to get even smaller isn't doing you any good because that's swamped by whatever the fluctuations in ST are. So you want to balance those two things out. The first thing is analyze how long it takes to get the expectation to be small, and then look when is that about the same order as the fluctuations, and then allow the fluctuations to kick in and have the thing hit 0. So Malvina did mention this, the drift of ST is given by this expression here. In the beta equals, so the key point is, well, if beta is less than 1, this is giving you a contraction. But when beta equals 1, when you expand the tangent, the ST over n term is the first order term of the tangent is going to cancel exactly because beta equals 1 with ST over n. And so the dominant contribution here to the drift is actually coming from the next order term, which is an ST over n cubed term there. So, pretending that it gives you an exact equation for the expectation of ST, you just have this difference equation here. You can skip all of this stuff in between. That's just how you analyze a difference equation. It's fairly standard. But the key point is, again, I want to balance off the time it takes for the expectation to be small with whatever the fluctuations are that are left over after I get the expectation small. So let's say I want to get the expectation of ST to be n to the alpha minus 1. So here I'm thinking of ST as the average magnetization, so I'm dividing by n. So you can think about this as how long to get the total magnetization, the sum of spins, to be n to the alpha. And the key thing is once you analyze this difference equation, you see that you need n to the 3 minus 2 alpha steps in order to get the expectation of ST to be n to the alpha minus 1. So we'll see how to choose this alpha correctly so that you get the optimal thing in just a moment. Okay, so once you get the fluctuations, the average of ST down, you want the fluctuations to take over, and NST is the total magnetization. Okay, once it's small, you can compare it to simple random walk. Its fluctuations are of the same. Its behavior is very similar. It's downwardly biased, but once it's close enough to 0, the dominant contributions are just coming from its noise. And so if NST is order n to the alpha, for example, if a simple random walk is at height n to the alpha, the amount of time you need for it to actually hit 0 or come close to 0, if it's not a simple random walk, is the square of that. So you need n to the 2 alpha more steps. Okay, so a simple random walk hits at height n to the alpha, hits 0, and n to the 2 alpha more steps. All right, so the total time to hit 0 is the time to get the expectation down to n to the alpha, which is you need n to the 3 minus 2 alpha steps, and then you wait until the fluctuations push this thing into 0, and that gives you the n to the 2 alpha. Okay, so you want these powers to be equal to get an optimal bound here, so take alpha equals 3/4, and this gives the time until you hit 0 is, with high probability, very close to n to the 3/2. Okay, so I explained how long it takes for one copy to hit 0. Now, how do you couple together two copies of this magnetization chain? Well, you use this reflection coupling. So how does this work? Well, you first let the two walks evolve independently of each other, and you wait until their absolute values agree. Now, you could be very unlucky here, and the walks could jump over each other, but just ignore that, because actually we only need this coupling to work with uniform probability, because we're not asking for exact constants in our mixing time. So when they come to within distance 1 with some fixed probability, they'll actually collide. I'm talking about the absolute values. So you wait until those absolute values agree. It does that with some positive probability. And once they agree, then you do the obvious thing where you reflect the two copies. Now, because there's this obvious symmetry in the Ising model between pluses and minuses, the magnetizations chains, starting from say, if I change the pluses to minus, I just reflect the walk. So then I just reflect these two walks until they hit zero, until they collide necessarily at the time the first one hits zero. Okay, so the time to couple is actually just bounded by the time it takes for the first walk. Let's say the walk one is higher in absolute value initially to hit zero. Okay, so that's the reflection coupling. Now I mentioned before, once you get the magnetizations to agree, that's the main thing. To get the full configurations to agree, you only need n log n steps. So let me explain how to couple, given you have the same magnetization, how you get the configurations to agree. So here I have two different configurations with the same magnetization. The first line is one configuration, and the second line is another. Let's say black dots are plus ones, and the white dots are minus ones. So what I do is I just want to match up the plus ones with the minus ones, and I can do that because the magnetizations agree. No problem at all. I want to match them up so that at the same site, if I have agreeing spins there, then those guys are matched. So those first two guys are matched, and then the guys where I have disagreements, those are matched however I want to match them. It doesn't matter. All right, now let's say I pick a vertex at random to update that. If I pick, say the fourth guy, well, let's say I pick the leftmost guy here. Well, I can update, the marginals will be correct if I update those together, because first of all, the only thing that matters is the total sum of spins minus the spin at the vertex that I'm updating, which is what I said initially. So because the spin at the vertex I'm updating agrees, okay, the marginal distributions will be correct if I update those two guys on the left together. So the only issue is, what if I pick a site where the spins disagree in the two configurations? Well, the thing is, I'm not going to update the same vertex in that case. So, think of the algorithm as follows. First, pick a vertex to update in the top guy, and then update the vertex which is associated to that by this matching here. All right, so if I pick, let's say, the fourth guy to update in the top one, I'm going to actually update the third guy in the bottom one, and the marginals will be correct because the sum of spins minus the guys that I'm updating agrees in those two configurations. So notice here, if I update agreeing guys, I don't introduce more disagreements. They'll continue to agree. But if I update a disagreeing guy, I actually kill two disagreements. You see, let's say I update that black one there and its associated guy in the other configuration, then I flip those both to white, and I actually decrease the disagreements by 2. So you see that the probability I decrease the number of disagreements is just proportional to already the number of disagreeing sites. So, right. That says if I look at the drift of the number of disagreements, it's decaying like some constant times already the existing number of disagreements over n. And that's enough to show you that the expectation will be driven down to 0 if you just take t equal to be gamma n log n. So if gamma is very large, then this will be small. I'll just say briefly how the lower bound, well, it follows from, there's a set of states which is going to be very likely under the stationary measure, but not likely if you take a small constant times n to the 3/2 number of steps. And that follows from there's a central limit type theorem for the sum of spins at the beta equals 1 due to Simon and Griffiths, which says that Sn's scaled by well, if you're talking about the total magnetization, if you scale that by n to the 3/4, that converges to some non-trivial probability distribution. So if I talk about the average magnetization, it's not likely to be much, a very large constant times n to the -1/4. Okay. On the other hand, if I take a small constant times n to the 3/2 number of steps, well, the expectation, just using the, calculating, you have this difference equation for the expectation. Well, it's going to be a large constant times n to the 1/4. This constant is like 1 over the square root of gamma. Yeah, that should be a minus quarter there. Thank you.
You start from all pluses.
That's right. Start from all pluses. Yeah, so if you start from all pluses and you only go a small constant times n to the 3/2 number of steps, then the expectation is going to be n to the, a large constant times n to the -1/4. So you see the two distributions, the distribution after small constant n to the 3/2 steps is separated from the stationary distribution. Its stationary distribution is concentrated at a small constant times n to the -1/4. So that tells you that you have a lower bound also of order. The fluctuations, ST will be concentrated near its expectation in this case. Okay, so this is my explanation for the n to the 3/2. I'll just repeat the conjecture, which is all of this behavior we think, is special to the, well, we proved it's special to the complete graph, but we believe it's sort of generic. So if you have the critical value on a box, say BC, then at this time you should have mixing, which is worse than n log n. It's polynomial in the number of sites, and maybe this n to the 3/2 is actually maybe the 3/2 is the right power, at least in high enough dimension. So so we believe this is maybe generic. So I'll stop there, and thank you for your attention.
If I remember correctly, someone asked Malvina, do you know that you don't have a cutoff phenomenon in this case? And if I also recall correctly, she said, yes, we know that. Can you say any words about how you know there's not a cutoff phenomenon in this case?
Yeah, I think, is this in your paper with Jian? Yeah, so you can ask Eyal. He'll explain it to you.
So this, it really boils down to the same reason that you don't have cutoff for simple random walk. Once you get to the range of n to the 3/4, you have a constant probability of doubling where you are in time, which is another n to the 3/2. And then you just iterate that to show there's no cutoff.
Yeah.
In fact, there's another thing that you can see here, that the spectral gap is of the same order as the inverse of the mixing time. The relaxation time is the same order as the mixing time. And that always precludes cutoff or reversible change.
You don't mind another question?
No, go ahead.
Is, if you were to take temperatures that weren't constant, but are close to critical with the deviation depending on n, could you get exponents that range all the way from 1 to 3/2?
Well, Eyal and
that's also
so there's a so Eyal and Jian Ding have a follow-up paper where they analyze the dependence of this constant on beta and show how it behaves near the critical point. Yeah.
You have a scaling window of 1 over root n. Represent the mixing time as a continuous function. So instead of n log n, you get n over something log n delta squared, where delta is the difference between the two temperatures.
Is DC equal 4 part of the conjecture so that it agrees with the physicist Vogler?
Is what?
Right, that's a courageous. DC should be equal 4.
Right. Yeah, yeah. So, oh, right. So you mean where the mean field behavior kicks in? Yes. Yeah.
That's an actual conjecture, but there's nothing in our work that leads to that. It's just, where universality should hold, then the results for the complete graph should.
So if there's no more questions, let's thank the 3 speakers.